In example 4b, we will test the equation y squared is equal to x plus 9 for all three types of symmetry. But first, let's revisit example 2b to look at the graph of this particular equation just to visualize what type of symmetry this equation does have. That way, when we go into the algebraic testing, we kind of know what to expect. Okay, so at the bottom of page 3, there is our equation, y squared is equal to x plus 9. We graphed it out. You can see the graph there. So let's discuss the type of symmetry we observe from the graph here. Okay, so let's first take a look at x-axis symmetry. Again, you want to imagine that this graph is on a sheet of paper that you can fold along the x-axis. So you would be folding your sheet of paper along this red dotted line, and you're asking yourself, does the top part of the graph, would it lie on top of the bottom part of the graph if you were to fold the sheet of paper in this manner? And the answer is yes. Okay, so this graph is going to have x-axis symmetry. Okay, again, if this is a difficult thing for you to visualize, pick a point that's not on either axis and, apply kind of almost the algebraic test for symmetry here. Okay, so if we look at this particular point, this is located at 7, 4. Okay, and we know that if a graph has x-axis symmetry, that means the point in which the x-coordinate remains the same and the y value changes sign should also be on the graph. So if we're looking at 7, 4, that means that 7, negative 4 should also be on the graph, and we see it right here. Okay, so that kind of confirms that this particular graph does have x-axis symmetry. Okay. All right, so now let's talk about y-axis symmetry. Again, if this were a sheet of paper, this time you would fold it along the y-axis, and for it to have y-axis symmetry, that means the left side of the graph should lie on top of the right side. Okay, that doesn't happen here if you were to fold the sheet of paper in this manner. Okay, so this graph does not have y-axis symmetry. Again, you can kind of observe that with a particular point. We can again look at the point 7, 4. Okay, if a graph does have y-axis symmetry, that means the point in which the x-coordinate changes sign and the y-coordinate stays the same should also be on the graph. Okay, so that would be -7, +4. Okay, and if we look at that particular point, -7, +4, that is going to be right here, and it is clearly not on this sideways parabola. Okay, so this graph does not have y-axis symmetry. Okay, finally, we'll take a look at origin symmetry. Again, the most difficult one to visualize because you have to flip a point about both the x-axis and the y-axis. So the easiest thing to do is to, realize that if you're dealing with any point on your graph, then if you change the sign of both the x-coordinate and the y-coordinate, that point should also be on the graph for the graph to have origin symmetry. So if we observe 7, 4, that means that if this graph does have origin symmetry, then -7, -4, changing the sign of both x and y, that should be on the graph. Okay, and -7, -4 is right here. Okay, not on the parabola, so there's no origin symmetry here. Okay, so this particular graph has x-axis symmetry only. Okay, so when we go back to page 7 here and we do the tests for symmetry, we should get a yes only for x-axis symmetry. Okay, so I'm going to go ahead and write that this guy should have x-axis symmetry only. Okay, but we do have to confirm it with our algebraic tests. Okay, all right, remember to start out here. Okay, the equation is y squared is equal to x plus 9, but to make your life a whole lot easier, you need to rewrite this guy so that no exponents appear. Okay, so I am going to put this in a different color and in a box. Okay, the only piece of this equation that has an exponent on it is the y. You have y squared. So we're going to rewrite that as y times y to get rid of the exponent. Okay, that's got to equal x plus 9. Okay, when we do our algebraic tests, we're going to look at this purple equation in the box. Okay. All right, so let's get started with x-axis symmetry. Okay, for x-axis symmetry, we know that basically if we start with a point, Okay, since it's x-axis symmetry, x will stay the same and y will change signs. Okay, so we're going to go to the purple box here. Everywhere you see a y, you want to replace it with negative y. So instead of y times y, we're going to have negative y times negative y. And then that's going to equal x plus 9. Okay, that's the only replacement we need to make, okay, is the y's become negative y. Okay, now we need to simplify and see if we get the original equation back. Okay, remember, you can look as far as the original equation is concerned, you can consider the one in the box, or you can use this yellow one here as the original equation. They're the same. Okay, all right, so if we simplify here, negative times negative is going to be positive. Y times y is y squared. So we get y squared is equal to x plus 9. Okay, if you compare this blue equation that you are left with to the original equation in yellow, they are exactly the same. Okay, so we're going to conclude, yes, the graph of this equation does have x-axis symmetry. All right, so now we move on. Let's take a look at y-axis symmetry. So we know the rule for y-axis symmetry is that if you start with a point xy, the x-coordinate will change sign. You're going to keep y the same. Okay. All right. So we're going to go to our purple box. We need to replace every instance of x with negative x. Okay. So we don't need to do anything with the y. So we're going to have y times y is equal to, instead of x, we're going to make the replacement negative x. Okay. And then tack on the plus 9. Okay. Now we simplify to see if we get the original equation. Okay, y times y is y squared. That is equal to negative x plus 9. Okay, that's as far as we can simplify. If we compare this green simplified equation to the yellow equation, they are not the same. The yellow equation has a positive x and the green equation has a negative x. Okay, since we didn't get the original equation back, we must conclude that no, this graph is not going to have y-axis symmetry. Okay, finally, we need to do the origin symmetry test. Okay, so to test for origin symmetry, we need to make both replacements. Okay, so if you start with a point xy, both x and y need to change sign. Okay, so what we're going to do here is go to our purple box. You need to replace x with negative x and y with negative y. All right, so we will get, instead of y times y, we're going to have negative y times negative y. Okay, that's got to equal, instead of x, you're going to write down negative x and then tack on the plus 9. Okay, now simplify. On the left, negative y times negative y is positive y squared. Okay, on the right, you can't really do anything. It's just going to remain negative x plus 9. That's as far as you can simplify. Compare this purple simplified equation to the original yellow equation. They are not the same. Okay, again, you see the yellow equation with a positive x and you see the purple one with a negative x. Okay, so that tells us, since we did not get the original equation back, no, the graph of this equation does not have origin symmetry. Okay, so again, we conclude for the graph of y squared equals x plus 9, for that particular graph, it has x-axis symmetry only. Okay, and we did indeed observe that in example 2b.